All right, thanks a lot. Pavan in the last talk of the previous session gave a really nice overview of sort of the hydrodynamics of these stellar mass black hole tidal disruption events. This is kind of a new topic that a lot of us sort of haven't thought about before, so I want to sort of spend a bit of time at first just sort of going through sort of the basic motivation for why stellar mass black holes are present in globular clusters and why we think it's actually quite certain that these are undergoing these tidal disruption events in the first place. And then I'll talk a little bit at the end about sort of our initial guesses for what the electromagnetic signature might be and some potential detection prospects. Okay, so just very basics first. So globular clusters. So I'm talking about things that are similar to the Milky Way globular clusters. So there's roughly 200 globular clusters in the Milky Way. These are generally very old stellar populations, low metallicities, 10% of solar metallicity or lower. The low metallicity is really important because we think this means that these stars are undergoing reduced wind mass loss, potentially leading to more massive black holes than you would potentially get at higher metallicities. I'm talking about clusters with masses of 10 to the 5 to 10 to the 6 solar masses. So clearly lower mass than a typical nuclear star cluster in the center of galaxies, but more massive than open star clusters, for example, which aren't quite as dynamically active. As I said, there's about 150 observed globular clusters in the Milky Way. There's maybe another 50 behind the bulge that we can't observe, but probably are there. It's now known very well that essentially all galaxy types host populations of globular clusters. So these are very common types of systems throughout the universe. Okay, so black holes and clusters. The basic motivation for this is really motivated from just a stellar populations perspective. If you have a typical cluster with, say, 1 million stars at birth, assuming just a typical initial mass function, a group IMF or something, roughly one star out of 1,000 will be massive enough to collapse into a black hole. So for a typical cluster with 1 million stars, you can expect roughly 1,000 black holes to form from just the stellar evolution of the most massive stars. And these form within the first few to tens of millions of years of the lifetime of the cluster, just set by basically the main sequence lifetime of these massive stars. And these black holes, once they form, are much more massive than the other stars in the cluster. And because they're much more massive, they're very quickly going to sink to the center of their host through mass segregation. So this mass segregation is operating in any sufficiently dense, dynamically active stellar environment. This is well known in many different contexts. The mass segregation timescale for these black holes, which basically just depends on the mass of the black holes relative to other stars in the cluster and also the density of the cluster, is roughly 100 million years or so. So, when you're considering very old globular clusters today, 10 billion years old or more, this mass segregation happens very quickly relative to the lifetime of the cluster. So for most of the cluster's lifetime, the structure looks something like this. You have this subsystem, this dense subsystem of roughly 1,000 black holes in the center, and then sort of the normal stellar population out at the larger radii. So within this black hole subsystem, the density is very high. Black holes are undergoing many dynamical encounters with both each other and also with stars. And the sort of inevitable fate of the black holes in the center is for the black holes to slowly be dynamically ejected from the cluster. So the escape velocity of typical globular clusters is of order maybe 100 kilometers per second or lower. So it's relatively straightforward to essentially kick these black holes through gravitational interactions with each other in a way that causes them to be ejected. So over time, over the subsequent evolution of the cluster, we expect this initial population of roughly 1,000 black holes to slowly decrease over time. So then the sort of main question we can ask is how many black holes would still be present today that we could eventually observe and use as sort of signatures of the presence of these black holes. So this story has really started to get very interesting over the past decade in particular because there are now a number of observed black hole candidates in Milky Way globular clusters that I think motivate this story very effectively. So the first of these candidates came about 15 years ago. These are accreting black hole systems or potential accreting black hole systems that are observed via their X-ray and radio emission. So the basic idea is that for X-ray binaries, there's sort of this fundamental plane of activity exhibited by black holes, where the ratio of the radio to X-ray luminosity for black hole accretors is noticeably distinct from the ratio for neutron star accretors. So these black points are all a bunch of black holes observed in X-ray binaries in the Milky Way, in the field of the Milky Way. And then these colored circles here are the potential black hole candidates that have been observed in a handful of Milky Way globular clusters. So you can see the sort of position in this radio X-ray luminosity diagram is suggestive that the accretor in these systems is a black hole as opposed to a neutron star. So there's around 10 of these candidates in both Milky Way clusters and also in a few extragalactic globular clusters as well. But this is definitely uncertain because the physics of this accretion process is uncertain. I think the most robust evidence currently for black holes in clusters came just a few years ago. So this came from observations with the MUSE integral field spectrograph. This was a broad radio velocity survey of around 20 Milky Way globular clusters, basically trying to make radio velocity measurements of a bunch of stars to identify binaries. So in this survey, they identified one particular star in the Milky Way cluster, NGC 3201, that exhibited very large radial velocity variations. So they did follow-up observations, attained about 20 radial velocity epochs, and they constrained the mass of the companion to be a minimum mass of roughly 4.5 solar masses. So with radial velocities alone, you only get a m sin I, just a minimum mass. But very clearly, this minimum mass of about 4.4 is a stellar mass black hole. So this was actually the first stellar mass black hole ever identified through just a blind radial velocity search. So this was very exciting. And this MUSE survey actually then ended up doing follow-up observations of this cluster, and they found 2 more black holes in this cluster. So also orbiting main sequence companions that are luminous. They made radial velocity measurements. The second one of these has a minimum mass similar to the first one, about 4.5. And then the third one has a little bit larger minimum mass, about 7. So we have 3 dynamically identified black hole candidates in this one Milky Way globular cluster. So a very recent result just from last week, some of you may have heard, there is, of course, many of these detached black hole star binaries that have been observed with Gaia, astrometrically and also through radial velocity follow-up. So the first 2 of these black holes, Gaia BH1 and BH2, have lower masses, around 10 solar masses. I'm not going to talk about these. But this recent one, Gaia BH3, is around 30 solar masses. It's orbiting a low metallicity star, like less than 1% solar metallicity. And it's, I think, very intriguingly, it's observed on a halo orbit and also in association with a known stellar stream that we think likely came from a disrupted globular cluster. So the fact that this is very massive, the most massive non-LIGO stellar mass black hole that we know of, the fact that it is its sort of orbit and it's associated with this stream is suggestive of the fact that it formed dynamically, is also very potentially evidence that globular clusters are being formed in globular clusters dynamically. So ask me about this source later. I'm not going to talk about it much more today. We think also that probably essentially all Milky Way globular clusters, based on what we know from n-body simulations of black holes in these systems, have black hole star binaries present in their cores today. So another thing that I'm involved in is a much more extensive radial velocity search of a large number of Milky Way globular clusters using both Keck and Magellan to identify additional stars with radial velocity signatures suggestive of black hole companions. So I think there's a very good chance that in the coming years, maybe 10 years, we'll identify additional black hole star binaries in clusters. Okay, so with this sort of background in mind, hopefully I've at least somewhat convinced you clusters do indeed have black holes, both today and also throughout their lifetime. So what are the implications? So number one, when black holes are present in a cluster and they form this dense subsystem of black holes in the central regions, these black holes, as they interact with stars, are a really large source of dynamical energy in the cluster. As the black holes interact dynamically with stars, they're constantly kicking the stars, transferring energy into the stars, and this essentially heats the cluster from within. So we can use things like surface brightness profiles of clusters, measured core radii, half-light radii, to potentially identify clusters that we think might have large populations of black holes in their center as a result of this sort of black hole heating. Another really exciting implication, when you have black holes in the center of the cluster and interacting with other black holes, this can naturally lead to pairing up of black hole binaries and ultimately gravitational wind spiral and mergers. So there's been a lot of work on looking at whether or not the gravitational wave sources from LIGO Virgo, if any of these, some of these could have formed dynamically in globular clusters. So Fully is going to talk a little bit more about this and sort of the implications of these collisions with stars that might play a role in the gravitational wave story. And then the third big thing, which is sort of the focus of this talk, is, again, if you have black holes dynamically interacting with stars in clusters, which we know of because we've observed black hole star binaries in clusters, this naturally can occasionally lead to sufficiently close passages between the black holes and the stars for the stars to be disrupted. And this potentially would lead to a tidal disruption event, potentially a bright electromagnetic signature. So the sort of characteristic radius for this is just sort of the classic tidal disruption radius. One of the obvious main differences between the sort of classic massive black hole TDE is the black hole to star mass is much closer to unity in this case. So the tidal disruption radius is only a factor of a few times larger than the actual radius of the star itself. So this immediately is a big difference between the sort of typical TDE we're used to thinking about. Okay, so first just some demographics. So this is basically looking at a large set of n-body simulations similar to the Milky Way globular clusters that include populations of black holes. And we're simply counting up how often a star passes within this characteristic distance of a black hole. So this plot here on the top left, this is basically showing the mass of the star that's disrupted versus time of the disruption event. This is just for, again, a population of Milky Way-like globular cluster models. The black points are all main sequence stars that are disrupted. So this is by far the most common case. About 90% of these are involving a main sequence star. Makes sense just because these stars are by far the most dominant population in the cluster. This track here I'm showing on the top here is the evolution of the turnoff mass in the cluster over time. And you can see, not surprisingly, the giant disruption events track this main sequence turnoff mass as they evolve. So about 10% of the disruptions are involving giant branch stars. And then you also have a handful, at least in this set of models, of tidal disruptions of white dwarfs. So I don't think it surprises anybody that those are very rare just because the white dwarfs have a very small cross-section for tidal disruption. So the typical values of the masses involved here for the star itself basically just tracks the IMF. So the most common types of stars from just the mass function perspective are going to most commonly be disrupted. So low mass stars, less than a solar mass, M dwarfs, these are sort of typical event involved in these. And the black hole that's disrupted is generally 10 to 20 solar masses. So this bottom plot here is showing basically the black curve is the distribution, the mass distribution of all black holes in these models. The green histogram are the black holes that merge with other black holes, so the potential LIGO sources, and then blue are the TDE black holes. So the main point I want to emphasize here is that the TDEs generally involve lower mass black holes relative to the LIGO sources. This is basically because the most massive black holes tend to sink the deepest in their cluster potential and preferentially interact with each other, preferentially undergo mergers, whereas the lower mass black holes aren't able to sink as much through this mass segregation process, so they're more likely to be found in these sort of outer parts of the black hole subsystem where they can interact dynamically with the stars. So more massive black holes generally undergo mergers with black holes, lower mass black holes undergo the tidal disruptions. And then from a rates perspective, again, from these n-body models, we predict, similar to what Pavan said, roughly one of these TDEs per million years in the full population of Milky Way globular clusters. If you extrapolate to sort of the local universe, using our best guess for the distribution of globular clusters in the local universe, of order 10 to 100 per gigaparsec cube per year. So definitely less than the core collapse supernova rate, definitely less than sort of the supermassive black hole TDE rate, but still certainly high enough to potentially produce a high detectable rate. I'm going to kind of skip over this. So our group has done a lot of hydro simulations similar to the stuff Pavan was talking about. A lot of the similar results are recovered. This is an example of one of these tidal capture scenarios where you have a partial disruption and then the partially disrupted star remains bound and undergoes additional passages. The main point that I want to make is that the general outcome of these, because the relative velocity at infinity is very low in globular clusters, these are essentially parabolic encounters. So naturally, you're going to generally retain a lot of the mass in these encounters, whether it's a tidal capture where you actually remain bound, the partially disrupted core remains bound, or if a lot of the disrupted debris ends up, being bound to the black hole itself. So qualitatively, the outcome of these is sort of a thick, rotating torus of material around the black hole. And I think from just a qualitative perspective, it really has a lot more in common with a collapsar or a massive black hole than it does with a supermassive black hole TDE, just because of the time scales involved. So the main time scale of interest here, I think, is sort of looking at the ratio of the fallback time of the disrupted debris to the viscous time of the disk that ends up forming. So this plot here is showing a bunch of different models with different sort of penetration factors. So highly penetrative encounters on the top that lead to a full disruption of the star, and then on the bottom, partial disruptions where the star is only partially stripped and only a little bit of mass ends up being bound to the black hole. So this has been looked at a lot for supermassive black hole TDEs, that partial versus full disruptions lead to a different time evolution in the fallback rate. So that basic evolution is recovered here. The main point that I want to emphasize, though, here is the sort of time scale for the peak amount of fallback. So this is typically the characteristic fallback time for these is of order hours or at most a day. So very short relative to massive black hole TDEs. And sort of doing a very simple thing for the sort of viscous evolution of the disk that ends up forming, the fallback time is comparable to or even less than the viscous time of the disk. So the fallback time is not really the dominant time scale in these cases. It's really the viscous evolution of the disk that determines the ultimate features of the evolution of these and potentially their light curve. Okay, so sort of our basic, at a cartoon level, estimate for what the electromagnetic signature would be. Let me see how I'm doing on time. Oh, perfect, okay. So again, you have some fraction of material that ends up bound to the black hole. It's almost certainly less than a solar mass, just because, again, the mass of the star themselves that are disrupted are pretty small. Assuming a sort of typical sort of alpha prescription for the disk, you can estimate viscous times of order a day or maybe a few days for the time scale for which most of this material should be accreted. And the main punchline is that the m dot, the mass accretion rate you get for these disks, is orders of magnitude above the Eddington limit. So these types of super Eddington flows have been looked at in many different contexts. Again, I think qualitatively a really good sort of thing to keep in mind is sort of a massive star, the formation of a black hole or a neutron star at the end of a massive stellar evolution. A collapsar is very, very closely analogous. We generally expect that when you have these very highly super Eddington flows that most of the disk mass is going to be launched from the disk as a wind, and a very small fraction will actually make it to the black hole itself where it could potentially be accreted. So a typical way that a lot of people have parameterized this is the ratio of the gravitational radius of the black hole to the disk radius, which is about a solar radius. So this ratio is about 10 to the minus 5. It's a very small fraction. And then we usually use this sort of exponent s, which basically just parameterizes how much mass actually makes it to the black hole radius. I think for any reasonable assumption about this parameter, which is very uncertain, suggests that 1% or less of the mass in the disk ends up making it all the way to the black hole. So this means that a lot of the disk ends up being launched as a wind, and then this produces a very dense circumstellar material around the disk that could potentially lead to reprocessing of the accretion energy produced by the small amount that is accreted onto the black hole. So I'm not going to go through the exact details of this model, but basically we've set up a basic radiation hydrodynamics model that tracks the fallback of material from our hydrodynamic simulations onto the black hole itself and the formation of the disk evolution over time as it expands and evolves viscously, and then also the amount of material put into this wind and the radiation hydrodynamics of this wind itself. So basically what we can do is, assuming some fraction of material that makes it to the black hole, we can estimate some accretion energy, which is basically the engine that powers these transients. We can estimate the radius at which this accretion energy is absorbed and then reprocessed by this dense wind from the disk itself, and then the corresponding luminosity, color, and time scales involved. So the main punchline of this is we expect, again, subject to the uncertainty surrounding the exact amount of material accreted, these could potentially produce reprocessed power transients of order 10 to the 40 up to maybe 10 to the 45 ergs per second, blue to UV in terms of their colors, with rise times of order a day to a few days. So I think Matt Nichols is going to talk about this a little bit more on, I think it's Friday. So I'll just touch on this briefly. There have recently been a handful of potential transient events that could be signatures of these. So these have been identified with a few different all-sky surveys. So all three of these events are found in massive quiescent elliptical galaxies, which are really good sites for having many globular clusters. I think each of these galaxies has of order 1,000 globular clusters or more in their halo. So they're quiescent, so it's hard to explain these with sort of massive star models just because there's not really much star formation going on. These also have very high offsets from their hosts of order a few to even 10 kiloparsec offsets. So massive black hole TDEs are also tricky just because of the high offsets. And then from a light curve perspective, again, subject to the uncertainties surrounding the details of how much mass is actually accreted, I think the types of models that we've been running for these events can reasonably span the range exhibited in these events in terms of the light curve evolution and the peak time scales. Kind of a cool thing is that JWST could actually resolve a host star cluster at the locations of these events, so this could potentially provide a very clear way to test whether or not these are actually TDEs in star clusters. And then I'll also just mention very briefly, Vera Rubin, Ultrasat, many upcoming all-sky surveys can really potentially detect a lot of these events. Okay, so that's everything. I'll leave my conclusions up. You can read those, and happy to answer some questions.
Let's see. I'll let people start out for questions. I guess I'll ask a sort of a general question. In trying to compare these events with the ones around more massive black holes, like very generally, what quantity should I think about as just kind of simply scaling with the black hole mass? And where do you get these kind of interesting regime changes, like the thing you're talking about with like the disk wind and some things like that, as far as like losing much more of the mass? Or
so compared to like the supermassive black hole TDEs, yeah. So somewhere in between at like an intermediate mass black hole would be where you would start to have a clear turnover between, again, something that's like a massive TDE-like versus, again, something more like a core collapse supernova type event like these. So maybe this could be a really interesting way to look for and search for IMBHs in the first place. Of course, those are already a contentious topic and very uncertain in their own right. So, but yeah, somewhere in the neighborhood of, I'd say, 1,000 solar masses should be where this transition should start to happen.
Yeah, thanks. All right, go
Hi.
ahead.
Going back to the torus that you form after the disruption of the star, you said that is very analogous to the collapse scenario. But there, those super Eddington accretion disks for photons are advection dominated, and then they become so hot that actually they start being cooled by neutrinos emission.
Yeah.
So why don't you have the same here?
Yeah, so I thought about this a bit, and I'm still not certain I've convinced myself either way or not. I think so the main difference there is that you have like a very much denser core, so the material that's accreting around the black hole itself in a massive star regime is going to be a much higher inflow rate than you have here, potentially. So I don't think these are going to be high enough for it to be in the
so which accretion
cooling.
rates do you get?
Which
accretion rate do you get, like 0.1 solar mass per year or less?
Of order a solar mass per year, maybe
so
a little bit higher.
that is exactly the accretion rate in the collapse.
No, it's the neutrino cool, you have to be above, say, 10 to the minus 3 per second.
Exactly.
Oh, so that's right. Yes, that's right. It's much less.
And also,
Okay.
these have
You
much
answer.
more angular momentum, so the m dot that actually gets down is much smaller. So
Yep, definitely.
Thanks.
I mean, if you had one of these with a more evolved star. Yeah, exactly.
Thank you for the nice talk. I was wondering if you could say a little bit more about how you treat reprocessing.
Okay. So basically, and yeah, we can chat more about this, and I can show you the specific details. But so you assume some fraction of material that is accreted onto the black hole, and then basically the rest we're assuming is launched into this wind. So then you basically, over time, you have some density profile for the wind. And then you also have this engine power from the accretion itself based on how much we're assuming is accreted. So then you basically calculate where the diffusion time in the wind is equal to the dynamical time, and you calculate a trapping radius, and then you assume that basically you have adiabatic expansion out to the trapping radius, so the engine power is reduced as it expands out the trapping radius, and that gives you your sort of emerging reprocessed luminosity. And then you can calculate like the color, the temperature and the color inside the trapping radius as well over time, and that gives you your light curve.
Thank you.
Thanks, very nice talk. Just a curiosity, I wanted to know about the observational constraint about the light curve of the comparison between the light curve of micro TDEs and micro tidal disruption event, considering the difference between the mass of the black holes involved, and if there are some differences that you can get or some constraint, I mean.
Yeah, so I mean, I think again the time scale, the main time scale involved for what the shape of the light curve is just the viscous time of the disk, which is uncertain. I mean, I've just used a simple alpha thing here to sort of motivate this, but so that's dependent on the disk radius. So the penetration factor of the disruption, how big the disk is, how much mass is in the disk based on how much mass is stripped. So all of these things affect sort of the viscous time and then actually the evolution. And then also the reprocessing, the time scale for the reprocessing depends on how much mass is launched into the wind and stuff. So yeah, it's a long-winded way of saying it's complicated, and I think there definitely is uncertainty and could be a large range in typical time scales involved.
Okay, cool. And do you expect with the next survey and the time domain astronomy to increase, I mean, the number of TDs that we could detect?
Definitely. I do think that the one thing that I feel pretty confident in saying is that these are pretty fast events relative to massive black hole TDEs. So of order maybe a week or a few days. So yeah, like something like Rubin, which has a much shorter cadence, is going to be really ideal for potentially finding these.
Great. Cool. Promising. Thanks.
I have two questions. One quick one on the rates. You quoted the rate. Is that for single encounters, or does that account also for binary scattering or whatever?
This is singles and also binary encounters. So, but this is assuming, these models were assuming a 5% binary fraction for all stars, which is sort of a lower limit you could assume. You could definitely imagine more massive stars were in binaries. So Fulia is going to talk about this a little bit. If you boost the binary fraction, that gives you, I mean, not orders of magnitude more, but it increases the rate by maybe a factor of 10 if you really increase the number of binaries.
And a question on the light curves that you just showed with the power law decays. Plotted next to it.
This?
Yeah, is this, what's the reference for this figure?
Oh, sorry.
Is that yours or?
Yeah, sorry, sorry, I keep showing the video.
Sorry, that's not my question.
This paper, it's
okay, that's fine.
Yeah.
Is that unevolved stars or what evolutionary stage are they?
These are just main sequence stars.
Yeah,
so these are actually polytrope models.
Yeah, I'm interested. So with Theo, we did a lot of scattering experiments with the same setup. Yeah, so he was the advisor of Pavan. So if the stars are a little bit more evolved, there's more room for these partial tidal disruptions, and the first encounter to actually be quite mild, and the second encounter to be the core of the star. So we opened yesterday discussing this double flaring things for supermassive black holes, but I'm curious whether the pre-flare can be light and the second flare can be much more dramatic.
I mean, you can kind of immediately get a sense from something like this. And the time scale for, by the way, the orbital period for this is like a few days. So you could easily imagine these leading to successive flares. I mean, you could get multi-peak things.
So Theo has this cool result I found cool. I don't know if that's mentioned before. So if at the first passage you lose a little bit of mass, but a lot of angular momentum, and at a relatively big impact parameter, but then you come back and you have lost most, and there's almost a radially heading for the black hole. And so this is a really weird opposite order. Anyway, for the variability, as soon as people start to look for light curves of any kind and already assume it's a nice rise in decay, they may be quite wild with precursors.
So the light curve stuff I talked about is all sort of just looking at like one passage, but a lot of these are going to have multiple passages, so I think that there's some fun stuff to think about in more detail.
So I hope a few of us stay longer, but I think some of the things to figure out is how diverse are they and how can we find these the crazy ones in decent data sets. But anyway, thanks. Very nice talk.
Great talk. So I have a question about the JWST follow-up that you said towards the end. Okay. So what kind of follow-up do you plan in detail? So do you want to figure out the redshift of that source? And
So
check its consistency, or
we know the redshift from, because the host galaxies are observed. You can actually resolve and observe a host stellar cluster with JWST at the position of these, if it's a massive enough cluster. So if the cluster is below 10 to the 5, it probably wouldn't be bright enough. But if the host cluster is above like 10 to the 5 solar masses, which is a pretty typical cluster, you can actually observe it with JWST at the redshifts of these events. So that would be like the best. I mean, that would be very convincing that these are powered dynamically.
Photometry is good enough.
Huh?
So the photometry is good enough to just conclusively say.
Yeah, so I think Matt will probably talk about that more in his talk, but it should be. Yeah.
All right, let's thank Kyle again.